Now that we have laid out the elements of propositional calculus, that is, propositions, operators, groupers, and this overall idea of the proper use of these symbols so that we construct well-formed formulas. Now that we have our elements laid out, we can look more closely at the five operators as functions and see how these operators behave. So let's start with the idea of a function. Let's look a little bit more deeply into that. So one of the things we pointed out earlier is that if we have an assertion about the world like, I have a headache, that assertion has a truth value based on the condition that the world is in. And in other words, that assertion is either true or false. If we focus only on the values that propositions can have, then it's obvious that propositions, any proposition, can have one of two truth values, true or false. So what we could say about that is that the domain, if we use the language of mathematics, the domain of a proposition is the set of values, true or false. I want to reiterate again that we don't have to know which truth value a proposition has. All we have to know is that a proposition does have a truth value. And this, incidentally, is one of the reasons that we like to use variables to represent propositional constants, because it gives us the flexibility and a little bit of abstraction so that all we're really looking at is the way the truth values behave. So let's consider the negation. If we look at, it's not the case that P, and again, I'm using P just to sort of highlight the fact that we have a particular syntax at work here. The negation sign operates on everything in the box, and what's in the box has to be a proposition or a well-formed formula, which we can represent by a variable. So if we focus on this, what we realize is that depending on the truth value that we put in for P, the not is going to take that value, do something to it, and then give us an output value. That's essentially the same idea as the notion of a function in mathematics. F of x is the way we often represent functions. We put a value in for x. The f function does something with that value, and it gives us an output in the form of some other value. In this case, both the input values, in other words, the domain, and the output values, that's the range, are the same, namely the two values, true and false. So if we think about the behavior of this expression more specifically, if we assign true to P, then it's not the case that P is going to give us as an output false. If we assign false to P, or in other words, if P has the value false, then it's not the case that P is going to have the value true. So there's a convenient way for us to represent this behavior using a truth table. So I'm going to construct a truth table, and then we're going to learn how to construct a truth table. I'm just going to show you an example of a truth table. So this is the input column. This is going to tell us what we're putting in for the value of P, and this column is the output, in other words, what not does to the input value for each of the values that we input. Okay, and now, what values are we going to input? Well, since the domain of a proposition is always either true or false, all we have to do is make a row for what happens when P is true, and another row for what happens when P is false. So, with this input, each row is going to represent one application of the operator. So on the first row, P is going to have the value true. Not P is going to give us the output false. For the second row, P's going to have the value false, and not P will output the value true. So if you think about this truth table we just constructed tells us exactly how the not operator, in other words, negation, behaves. In a sense, it's a definition of negation. Why is that? Well, think about it. This operation is, according to its syntax or according to its schema, its logical form, it is the same as this. It's telling us it's not the case that whatever is in the scope of the negation sign, and what we're saying is in the scope is a proposition, and that proposition can only have one or the other of these two values. So, in a sense, this truth table captures every possible situation with respect to the variable P. Why is that? P can only be either true or false. We have one row for each of those possibilities, and therefore we're giving every possibility in terms of an output that the negation of P could possibly give us. Another way to think about it intuitively is there is no other behavior, no other result we could get than these two outputs, these two rows. They correspond to two inputs. Those are all the inputs there could ever be. And so the outputs are, as we say, exhaustive. In other words, there's no other behavior that can happen than what we capture in here. So that's why we think of this as a definition of negation. Now let's look at another operator. This time let's look at the operator P and Q. Now we have a different problem, which is we have two variables. If we have two variables, we need to consider more possibilities because, as we learned in our introduction to propositional calculus, P can be either true or false, and Q can be either true or false. So we have to consider every possible combination of values that P and Q could have. So now I'm going to show you an algorithm that ensures that you cover all the bases in terms of possibilities. And it's based on a little math, and here's how it works. So we have two values that each proposition could be, true or false. And so what you want to do is count up the number of variables you have, not the number of instances, not how many times a variable is used, but the number of discrete variables you have. In this case, we have only two, and you use that as the power. So 2 to the second power, you remember that means 2 times 2. 2 times 2 is 4, and that is the number of rows we need. So you can indicate this like that, 4 rows. Now, to construct the first column of rows, again, we're figuring out what all the possible inputs are. What you want to do is start at the top of this column and alternate by ones. So we're going to have true, false, true, false. So notice alternating by ones. Then for each additional column, you double the alternating factor. So if the first column alternates by ones, doubling 1 gives us 2, so we do true, true, false, false. All right, if we had another column, we would double the alternating factor again, and it would be alternating by 4s, then by 8s, then by 16s. You get the idea. Same thing here. If we had 3 distinct variables, then it would be 2. That's our base number of values, true and false, to the third power. That's 2 times 2 times 2. That means 8 rows. If we had 4 variables, it would be 2 to the fourth power. That's 2 times 2 times 2 times 2. That is 16, and so on. And this tells you the number of rows you need in each case. So the value of doing this algorithm and constructing the table is that we can now be sure that we have exhausted every possible set of inputs that this expression could have. So if you look down this list here, it's like flipping 2 coins, right? You might have 2 tails, a heads and a tail and a heads, or 2 heads. But the idea is there are no other possible combinations that could ever turn up. Same thing here. So now, intuitively, we've already worked out what conjunction does. If it's similar to the English word and And what it means is that the two propositions that it joins together both have to be true for the overall result, the and proposition, to be true. So think back to our example of I have a headache and I'm hungry. The only situation where this proposition is true as a whole is when the two individual propositions that build it are both true. So that's what we can say here. If P is true, so again, for the first row, it's our first set of possibilities. If P is true and Q is true, then P and Q is true. So just to talk you through this first row, on this side, so I use a double line to separate the inputs. This is the input from the output of the function. So that's the output. And these then are input values for P and Q. So if P is true and Q is true, P and Q is true. For the second row, if P is false and Q is true, then P and Q is false. For the third row, of course, that represents another possible combination. If P is true and Q is false, then P and Q is false. And for the fourth row, if P is false and Q is false, the final set of inputs, then P and Q are false. Now, once again, if we look at this truth table, what we can say about this truth table is that it actually constitutes a definition of the function conjunction. And just to reiterate this, the reason is because there is no other behavior that we could find. These are all the possible combinations of inputs that P and Q could give us. And because that's all the combinations there are only these specific outcomes. So this truth table exhausts all the possibilities that there could ever be for inputs. And because of that, it tells you every possible behavior that the conjunction could ever have. All right, excellent. Now, let's go on and look at the behavior of P or Q. P or Q is quite similar to the English word or, except for one complication. So let's start by building our truth table, and then we'll look at what that complication is. So notice, I have set up the expression that we're evaluating. We're going to try to figure out what the output is. It's basically a calculation, right? We've set up our input columns. We need to figure out how many rows. So we start with two values, true and false, and we have two distinct variables, P and Q. So it's 2. 2 to the second power is 4. So we need 4 rows. Now we start with the first column and alternate by ones, true, false, double the alternating factor, true, true, false, false. Now we're ready to start thinking about truth values. But here is where we have our problem. Think about the English word or. Suppose we were having a party and I said to you, you can have cake or pie. So let's abbreviate. You can have cake and you can have pie. So this represents you can have cake or you can have pie, or in a little bit more colloquial English, you can have cake or pie. Now, what does it mean to say to you, you can have cake or pie? Well, it depends on how you interpret or. One interpretation of or is that you can have cake or pie, but not both. And sometimes people indicate that with inflection. Maybe they make a face. I know when I was a kid, my mom used to represent that by raising her eyebrow and adding an inflection to it. Like she would say to me, you can have cake or pie. Now, I know you can't see my eyebrow going up, but I'm sure you have seen people make a similar gesture. So what does that actually mean, that inflection? Well, if you think about it, our possible truth values for like the you can have cake or pie, you can have cake and no pie, you can have pie and no cake. So for these two possibilities, I'm telling you the truth when you have cake but no pie, or you have pie but no cake. But then if you have neither, then It's not true that you can have cake or pie. But the question really comes down to what happens if you try to have both. With the inflection, the answer is false. In other words, I'm not allowing you to have both. On the other hand, there's another way to interpret this, which is a little more generous, and usually in English we say that with a different sort of inflection. Like, you can have cake or pie. And then if somebody wants to have a little bit of both, that's okay. Now, some languages have separate words for this. So, for instance, in Latin, the word vel means the more inclusive kind, the kind of or where you can have both and it still turns out okay. They have a different word for the type of or that means you're excluding having both. And that's where we get our names for these two interpretations of or. This first word, vel, is where we get the little symbol for or, P or Q, and we call that inclusive. The inclusive or is the or that includes the possibility that that you can have both. This word out in Latin, or that English word or with inflection, we call that the exclusive or, because it excludes the possibility of having both. So with this in mind, we can construct a truth table for this type of or that we're going to use, which is the inclusive kind. And we can see that if the two inputs in the first row, if the two inputs are both true, then our inclusive or is going to give us true. If P is false and Q is true, then P or Q is true. If, on the third row, if P is true and Q is false, then P or Q is true. And finally, if both are false, then P or Q is false. And again, this defines disjunction, which we, just to remind you, which we interpret as the inclusive or. Inclusive means it's a little bit more generous and it includes more true possibilities than the exclusive or.